All right, good morning again, everyone. So just a quick reminder, available na yung problem set sa Canvas. So you'll have until November 1st, right before midnight, to submit your answers to it. Medyo may binagawang konti dun sa problem set. It still consists of a total of 4 problems, and then problem number 1 is required to be submitted. I mentioned na apat yung problems, pero in consideration of probably you have other problem sets to take care of before the reading break, I decided to reduce the number of items to be submitted by 1. So tatlo na lang yung isasubmit nyo. May apat na problems dun sa problem set. Number 1, yung problem number 1, kailangan yung isubmit, and then you only need to choose 2 out of the remaining 3. So pili kayo alin dun sa problems 2, 3, and 4. Pili kayo ng dalawa kung sino yung isasubmit nyo. And as I've mentioned in the instructions, walang extra credit pag nag-submit kayo ng lahat, pag sinubmit nyo lahat ng problems. So just choose 2 out of the last 3 problems, and then plus problem number 1, a total of 3 required submissions. Okay? So that would be over 30 points. Tapos sa pansin ko, dalawa lang pala yung problem sets natin for the semester, no? So yeah, that would be our midterm problem set. And then the other one will be before or right before the end of classes. So it will cover nga lang yung natitirang dalawang chapters nung course, pero medyo mas maiksi naman to compared to polynomial approximation. All right? Okay. So hopefully hindi siya ganoon kahirap, and at least mas magaan para sa inyo ngayon nung tatlo na lang yung submit niya. Okay? So now let's start talking about the brand new chapter in the course. So we'll start with module 6 today, which is basically the start also of chapter 2, which is numerical differentiation. Okay? So I just had a couple of typos here in the before you proceed section of the module. Late ko na realize na yung November 8 pala ay parte pa rin ng reading break. So the lab session for module 6 would be on November 15th, and then that will also be the deadline for the fourth problem for the fourth laboratory exercise. Though yung laboratory exercise 4 will be a combination of topics from module 6 and module 7. So yeah, so magsasabay sila sa November 15. But I'll try to upload the lab exercise part for module 6 earlier para masimulan niyo siyang gawin kahit hindi pa siya deadline, right? So para hindi kayo matambakan para sa November 15. So probably if you want, you can check it over the reading break. Hopefully I can upload it by then. Pero yun nga, hindi kayo required magtrabaho sa reading break, so you can just work on it after you come back by November 9. Makikita nyo na hopefully yung laboratory exer part 1 associated with module 6, but everything, the entire exercise 4 will be due on the November 15th, okay? Now, for module 6, here are our objectives. Number 1, we would like to derive a finite difference formula for numerical differentiation of a certain order. We'll start talking about it today. But incidental to deriving the finite difference formula is a determination of an upper bound for the error. So makakuha rin tayo ng upper bound para dun sa error incurred in numerical differentiation. Pero ngayon, ang madiderive lang natin ay yung part corresponding to the theoretical error. In succeeding modules, we'll talk about the error due to machine precision or to machine epsilon, kasi nakakadagdag din to dun sa instability or inaccuracy ng numerical differentiation formulas. And actually, medyo mas challenging ang numerical differentiation usually kasi napaka-unstable na numerical differentiation. And probably you can see it partly why dun pa lang sa pinaka-formulas na nadiderive natin. Okay? And then, of course, objective number 3 is to use numerical differentiation techniques in order to solve scientific problems. Okay. Now, the motivation behind the numerical differentiation schemes, again, ay nag-arise dahil dun sa common problem na nakita natin dun pa lang sa numerical uh, dun sa problem na nakita natin dun pa lang sa simula when we discussed the polynomial approximation. We said that the type of data or information we get from the real world or from experimentations or from observations are usually discrete in nature. So usually hindi given kagad yung functions na nakukuha natin na mula sa real world data, preventing us from using the tools that we learn from analysis. So, talagang papasok tayo dun sa unang step. Paano tayo gagawa ng isang nice enough function out of a bunch of data? So, for instance, gusto nating computein yung coefficient of friction required to, or the coefficient of friction between a flexible rope and a post around which we wrap a 5-pound restraining force. And then, kung gagawa tayo ng experimentation para mo-compute itong coefficient of friction, mu, magagawa lang natin ay i-measure yung amount of force needed to overcome a 5-pound restraining force at certain angles between the force itself and the post. So hindi natin talaga makukuha yung function of the force or yung function force in terms of theta by just looking at experimental or observation data. Kasi nga discrete lang yung makukuha natin. If you know it or just an additional info, coefficient of friction mu, ito yung proportionality constant between the rate of change of the force and the magnitude of the force. So basically, mu is the ratio between F prime and F, where F of theta is the function of the force with respect to theta. So ayan yung force na kailangan para ma-overcome yung isang restraining force given an angle theta. Okay. Now, again, para ma-compute si mu, it's a constant of proportionality, but it is defined to be the ratio of F prime and F. So, ang problema natin ay, pagka gusto mo itong i-measure, meron ka lang experimental data, gagawin mo si F, i-wrap mo sa yung kukomputin mo yung force na kailangan mo para ma-overcome yung 5-pound restraining force at given angles theta between the force itself and the post. Okay? So ang problema, paano tayo makakakuha ng function capital F out of this discrete set of data para mo-compute si F prime over F? Any suggestion? Or may naalala ba kayong method? How can we do it? Kasi yun nga, paano natin mako-compute yung mu following equation 6.1 where we only have a discrete set of data for f. Alam lang natin various values of theta and then various function values f. Any suggestions? Any ideas? Padali guys, recite kayo. Plus points to sa sa problem set. Ano kaya yung pwede nating gawin para ma-compute si mu? Pero ang alam lang natin ay wala akong chance na makuha yung actual function f kasi ang kaya ko lang ay discrete set of experiments or a discrete number of experiments from which we can get a discrete set of data. Anyone? Madali guys, sayang to. Bonus sa problem sets. Konting points lang pero pandagdag na rin. Oh, but you all can hear me, right? So thumbs up nga kayo kung naririnig nyo ako. Baka naman pala na-disconnect na naman ako. Okay, thank you. Ayaw nyo lang sumagot talaga? Or maaga pa para mag-isip masyado? Okay, so anyway, so again, and one thing that we can do is to take off from where we left off in Math 174 with these past few lessons that we had. kung meron tayong discrete set of data, tapos gusto nating makabuo ng isang function, then we can do polynomial interpolation or we can do curve fitting. Kasi nga kung discrete set of data lang yung alam mo, kailangan mo ng isang function f out of this discrete set of data, then we can take advantage of what we learned from the first chapter. We can get a polynomial model or a functional model for this discrete set of data by using interpolation or other form of polynomial interpolation. And that was the first approach for this particular problem. Halimbawa, ang gagawin ko lang, mag-experiment ako, and then I'll get the data similar to what is in table 6.1. So it says here that, for instance, if the angle between the post and the angle between the post and the restraining force is 0 degrees or 0 radian, then the force required to overcome the restraining force is 5 newtons. Okay. If the angle between the post and the restraining force is pi over 2, we're going to need 7.83 newtons and so on. Okay. So ito yung isang example ng klase ng data na makukuha natin by measuring the force required to overcome the restraining force, depending on the angle used between the post and the restraining force itself, right? So pagka ginamit natin itong discrete set of data na to, we'll get the polynomial interpolant, right? So gamit ka lang ng algebraic interpolating polynomial formula, you can get this equation for P, yung nasa 6.2. So ito yung makukuha nating polynomial model for that discrete of data, which hopefully will encapsulate enough information for the function f. Okay. So ngayon, meron akong function capital P, which is approximately equal to capital F. Of course, for angles theta from 0 to, what was the angle here? To 5 pi. Okay. And then ito yung gagamitin ko instead of the function f dun sa formula 6.1, right? Because again, formula 6.1 not only requires the function capital F, but also its derivative. But the nice thing about polynomial interpolation is that it will give up a polynomial whose derivative is again a polynomial, which is easily computed and is more computer friendly, right? So kung ito yung gagamitin kong P, papalitan ko lang sa capital F by this interpolating polynomial P, and then I will have a rough idea or I will have a rough estimate for the coefficient of friction. Okay? So ito si P, dun sa equation 6.3, kinompute natin si P prime. And then in equation 6.4, we form our approximate U tilde for the coefficient of friction. So kinompute ko siya as P prime over P, and hopefully this will be a good enough approximation for mu. Okay. The thing about mu is a constant. It's a constant of proportionality. Siya nga yung coefficient of friction. So what we'll try to do here is to plot U tilde as a function of theta all over the interval 0 to 5 pi. Okay. Tapos ito yung graph niya, yung nasa figure 6.1. So you will see here that except at some region before pi over 2, mukhang nag-stabilize na yung value ni U tilde around 0.286. So we can say that based on this model or the approximating polynomial or the interpolating polynomial model for f, we can approximate the coefficient of friction to be around 0.286, right? Meron lang konting anomaly dun sa boundary o malapit dun sa left endpoint nung interpolatory interval kasi yung value doon hindi nag-stabilize around this value, okay? So, yeah, that's one way to do it. So, kapag ka gusto pala nating mag-approximate ng derivative from a discrete set of data, all right? So what we can do is to get the polynomial interpolant, okay? Or use other interpolation like the cubic spline, which is continuous up to the third order. Pero medyo problematic yung cubic spline kasi alam natin pag kinuha natin yung fourth derivative niya, magzi-zero lang lahat. Right? So you can take the interpolating polynomial for your discrete set of data and differentiate it instead of and differentiate it to get approximate for the derivatives. Although may konting caveat yon, ma-inherit nung approximate derivative natin yung domain ng interpolating polynomial. Remember that the interpolating polynomial is only valid on the interpolatory interval. So dahil dun lang siya valid, yung approximate natin para sa derivative ay doon lang din valid sa interpolatory interval. Okay? So that seems to be a good approach to approximate derivatives, pero ang problema ay merong Runge phenomenon, right? So ayaw natin na malaki yung degree ng polynomial, and if you have, say, hundreds of thousands of data, then the model that you'll get using polynomial interpolation for that data will be of degree also in the thousands, right? So meron kang thousands of data, thousands of ang degree niya ay nasa thousands din. And we usually don't want to have that because that will be very prone to the Runge phenomenon. Okay. So ibig sabihin, mag-creep in din yung error na galing dun sa polynomial interpolation doon sa dun sa ating approximation of the derivative. Okay? So that's why we want to develop some more techniques on how to calculate the derivative numerically without without going through the pain of having that very large degree polynomial for the derivative. Okay? Tapos pwede natin gawin yung same approach as what we used for piecewise interpolants, wherein to consider just a few number of points at a time, and from there get the interpolating get the approximate for whatever we want to do. So kung maalala nyo sa piecewise interpolants, kinonsider natin interval by interval, dalawang points lang at a time yung ginagamit natin, so that we can paste together smaller degree polynomials, right? So ganun din sa numerical differentiation, pwedeng paunti-unti yung gamitin natin na points. Kung meron kang, say, 1,000 points, ayaw mong gumamit ng degree 999 polynomial para sa approximate dun sa function, which will give you a degree 998 derivative, right? Which usually doesn't make sense. Pwede nating sabihin, okay, para sa derivative at a particular point, gagamit lang ako ng dalawang points. Or para sa the derivative at one particular x value, I'm going to use 5 data points. And that's it. I will not use everything. Because anyway, kung matatandaan nyo naman yung definition ng derivative, siya yung slope ng tangent line. So we are only interested in computing the derivative using points that are very, very close to the particular number at which we want the derivative to be evaluated. Okay? And that's our plan for the rest of the module. Paano mag-derive ng differentiation formula using a preset number of data points to be used and the order of the error. Okay, but let's see one particular example. So kung ayaw mong gumamit ng maraming points, then pwede tayo mag-piecewise interpolation. Halimbawa, to calculate the derivative at, say, the point x0 or x sub 0 in the interpolatory interval, sabihin natin, okay, gagamit lang ako ng isa pang point, say x1. And then I'll compute the interpolating polynomial using the data points corresponding to x sub 0 and x sub 1. And of course, if you will use the Lagrange formula, then pag gumamit ka ng dalawang points, linear lang interpolating polynomial na makukuha mo. So that means if I do that, so I'll have this approximate for f. Okay, gamit yung dalawang points. So makikita nyo, ito yung or itong dalawa yung nagko-comprise ng linear interpolant for little f. Okay. And then this is the error term for the interpolation. Okay. And then we said na, okay, so ito, lower degree na siya kahit 1,000 pa yung points ko or data points ko. Ang nagmamatter lang naman yung malalapit kay x sub 0. So sabihin ko si x1 malapit siya kay x sub 0. Siya lang yung gagamitin ko pag-estimate ng derivative ni f. Okay? So here I form the interpolating polynomial together with the error term. Kaya kung mapapansin nyo, f of x is equal to yung nakalagay dyan. Hindi approximately equal to. Okay? And then what we can do here is to differentiate this f to get an approximate for the derivative. So ito lang naman ay linear functions yung unang dalawang terms. So f of x of 0 over x0 minus x1 is a constant. So kokopyahin lang natin siya sa derivative times the derivative of x minus x1 with respect to x. So linear function lang siya. So ang derivative niya lang ay 1. Kaya tayo nagkaroon nito. Do that also for the second term. You'll get this guy. And then differentiate the second term. You'll get this. Medyo iba lang yung form niya compared to what you'll get with if you use the product rule, but they will simplify to the same thing. Mas gusto ko lang yata itong form na to, kaya ganyan ko siya sinulat. Okay? Pero essentially, that is just the derivative of the error term. All right? So ibig sabihin, ito yung pwede nating i-estimate para kay f prime for any x between x of 0 and x of 1. In particular, if I plug in x equals x of 0, ito yung makukuha nating formula para sa derivative. So that means we can say that the derivative of f at x of 0 is approximately equal to this guy with error term corresponding to this. And if I will say let h to be the step size coming from x of 0 to x of 1, so this would be x1 minus x of 0, yung length ng interval consisting of x0 and x1. Okay. So ibig sabihin ito, pwede ko itong masulat as negative h. All right. So this would be your estimate, but do you think this estimate for the derivative makes sense, or at least this guy? Ito lang kasi yung estimate natin. Ito ay error term na. We cannot compute this exactly because all we know is that c is a number between x of 0 and x of 1. We don't know what exactly c is, pero guaranteed ng Rolle's theorem yung existence ng value ni c. Okay? So ibig sabihin, ito yung gagamitin ko pang computer, pang approximate dun sa derivative. But do you guys recognize this formula? Tatandaan nyo pa ba yan? Oh, any volunteer? Sagot na kayo. Ano tong formula na to? Does this ring any bell? Does this look familiar? And why does it make sense na siya yung estimate para sa derivative? Oh yes, Christy?
Po, mukha po siyang slope formula po. Tas kaya po siya nagme-make sense kasi po 'di ba ang sabi niyo po ang kailangan po natin sa derivative is slope po nung tangent nung function po. So ayun.
Okay, that's correct. Thank you, Christy. Yeah, that's right. So, etong nakabox na formula actually is the slope of the secant line, right? So, which makes sense kasi kapag kasi x1 ay papalapit ng palapit kay x of 0, yung secant line palapit siya ng palapit dun sa tangent line. Remember, para sa definition ng derivative, kunin ko lang yung limit nito as x1 approaches or as x of 0 approaches x1 o baliktad. As x sub 1 approaches x sub 0, then this will definitely be the definition of the derivative, right? And graphically, it makes sense kasi remember, kung ito yung function f ko, okay, ang slope ng tangent line, ang derivative kay x sub 0 ay yung slope ng tangent line at this particular point. So, halimbawa, kukunin ko yung slope nitong tangent line and the tangent line looks like this. So yung slope ng purple line na yan, siya yung magbibigay sa atin ng eksaktong derivative. But when we choose an x sub 1, right, somewhere near the neighborhood of x sub 0, halimbawa nandito si x sub 1, okay? So yung secant line joining x sub 0, the point corresponding to x sub 0 and x sub 1 will kind of look like this, all right? Tapos kung makikita nyo, mukhang malapit naman siya dun sa purple line. So their slopes should be close to each other. And we will get better and better estimates for the derivative if x1 becomes closer and closer to x sub 0. Kasi kapag yung dalawang points super lapit na sa isa't isa, then yung secant line passing through the points corresponding to these two x values will be very, very close to the to the tangent line. All right? And tingnan natin kung mag-make sense yun dun sa formula natin, kung makaka-capture natin yung observation na yon, na kapag si x1 palapit ng palapit kay x sub 0, dapat paganda ng paganda yung estimate natin para kay f prime. And actually, saan natin makikita yung, dito sa formula nito, saan natin makikita yung observation na yon? Any guess or any ideas? So palapitin lang daw natin ang palapitin si x1 kay x of 0, we get better and better estimates for f prime. Is that reflected in this formula that we have? Masyado pa ba talagang maaga? So, yeah. So, inom lang kayo dyan ng kape para ma-jumpstart ang ating ang ating mga sarili this morning. Though wala pa rin akong coffee, ano lang, water lang. Pero that observation that the approximate should get better and better as we make x sub 0 very very close to x1 is encapsulated in the error term, because if you look at the error term, meron siyang h, which is the step size, right? Or it has x0 minus x1. When x0 is very very close to x1, then this guy will be very very close to 0. So something close to 0 times a constant, so that will be close to 0. So yeah, yung formula na-capture niya rin yung idea na yon. But there's another thing here, but that will come with a cost. Kapag kasi x0 palapit ng palapit kay x1, ano yung magiging problema ko naman? Lumit nga yung theoretical error. Lumit itong term na to. But what would be a possible consequence of that? Na si x1 palapit ng palapit kay x0. Kasi sa numerical analysis, or in any numerical method, yung accuracy will always comes at a cost, right? So, posible na makahanap ka ng theoretical way on how to improve the error, okay? Pero laging merong kabayaran yon. So, parang alchemy to. You should get something of almost the equal value or even more to get a result, okay? So, ano yung consequence? Pag pinalapit ko si x sub 0 kay x sub 1, ano yung adverse implication niya or adverse effect niya dun sa overall approximation natin? Nasa formula lang din yan. Okay? So the problem there is when we make x sub 0 very, very close to x sub 1, tingnan nyo itong denominator. The denominator will also go to 0. And that's a big problem. Because if we will ask the computer to do division by something close to 0, there might be some problem there. Okay? Also, sa numerator, magkakaproblema rin tayo, especially if your function f is continuous. So, kapag kasi x1 ay malapit na malapit kay x sub 0, yung dalawang function values na yan, posible maging malapit na malapit din sa isa't isa. And if the difference between them is less than the machine precision, then ito ay pwedeng tingnan ni computer as something equal to 0. And then if x1 are also close, if x1 is also close to x0 with distance less than the machine epsilon, then the computer will think that the denominator is also equal to 0. So eventually you'll have 0 over 0, and then this estimate wouldn't make any sense. All right. So yun yung problema natin sa numerical differentiation. And actually, numerical differentiation is a very tricky process, and that's why kahit sa advanced applications, we try to avoid numerical differentiation. Okay? Kasi nga, ito yung mga problema. Laging yung decrease in the error, in the theoretical error, will come at a price which might induce some instability in the actual formula itself. Wala pa doon yung consideration ng round-off errors, which we'll do probably in Module 7 or Module 8. But let's forget about that for a moment, and let's just reserve that for later. So what we'll try to do for the rest of the day is to jumpstart our search for formulas for the derivatives, okay, for derivatives. And for that, we're going to use finite differences, okay? Pag sabing finite differences, ano lang siya, parang ratio ng differences, something that looks like this, okay? But now we will be taking advantage of a very classic result that you might have encountered in your elementary calculus classes, which is Taylor's theorem. Okay, Taylor's theorem gives us an expansion for a function f with continuous derivatives of all orders. Okay, so here you look at equation 6.6. This is the good old Taylor's formula that you have seen in math. Saan nyo ba ito nakita? 36 or 38? So merong expansion si f as an infinite series consisting of the derivatives. Kaya lang dito medyo siguro kakaibang form itong equation 6.6 kasi ang ine-expand natin dito ay hindi lang si f of x pero ang expansion na to is true for f of x plus h. Okay? And for f of x plus h, ito lang yung expansion niya. So you'll need summation of powers of h times derivatives of certain orders all over n factorial. And in expanded form, it will look like this. So starting today, please familiarize yourselves with equation 6.6, this formula, because we'll be using this repetitively, okay? And then the nice thing about Taylor's theorem, it also gives us a way on how to truncate this infinite series to a few finite number of terms. So sabi ni Taylor, so kung gusto mo lang gamitin hanggang order n, okay? So hanggang order n lang, halimbawa yung gusto kong gamitin dun sa summation, this will be a good approximation to the actual infinite series with this as the error. So kung ititigal mo yung summation hanggang dun sa may h to the power n, then the associated error is this guy. H to the power n plus 1 times the n plus 1 derivative of f evaluated at a number c for some number c in the neighborhood x of little x all over n plus 1 factorial. Ang idea kasi usually equation 6.6 is used for small h's. So kung h natin ay paliit ng paliit, ibig sabihin yung powers of h ay paliit din ng paliit. So yung contribution mula kay dun sa term na may h to the power n plus 2 ay insignificant na compared dun sa contribution ng term with power h to the n plus 1. The same thing goes, yung contribution mula dun sa term na may h to the n plus 2 ay masyado nang maliit and insignificant compared to the contribution of this guy. So we can say that this formula is of order big O of h to the n plus 1. So if you don't want to keep track of this messy factors, pwede nating tingnan, palitan natin to as a big O of h to the n plus 1. Remember, ang ibig sabihin lang ng big O ay yung behavior nitong term na to ay asymptotically bounded above by a multiple of h to the n plus 1. So, ibig sabihin, parehas lang to ng behavior at saka kay h to the n plus 1 in the long run. Okay? Kaya pwede nating sabihin to ay order n plus 1. Right? And we'll use this in order to get an estimate for the derivatives. Kasi kung makikita nyo, yung mga terms dito sa expansion, nag-i-involve siya ng mga derivatives. So we can take advantage of this expansion to get certain formulas for the derivative of f. Yan yung sisimulan natin with the first few examples today. Okay. And then let's try to, let's start by looking at recreating the formula we got from our two-point interpolation from the previous example. Okay. So para makuha ko yung or makapag-derive ng formula para sa derivative using 2 points, then for this 2 points, I'm going to use f of x and f of x plus h, right? So gagamitin kong dalawang points ay f of x at saka f of x plus h for some value of h which we want to be small enough to get a good accuracy but not too small that will cause instability. So saka na natin isipin ano yung optimal step size, meron tayong module para doon. Pero you can think of this as yung f of x sub 0 natin kanina. Kasi ito yung f of x1 natin kanina. Let's try to recreate the example we have from before. For that, we'll use Taylor's formula or Taylor's expansion in equation 6.6. Kung makikita nyo, pwede ko pala itong gamitin. Alright? So kasi nandiyan na si f of x, nandiyan na si f of x plus h, nandiyan na si f of x, nandiyan yung derivative. And then I'll just need to truncate the next few terms with higher order derivatives para hindi sila makagulo dun sa derivation. Okay. Pero hanggang saan tayo titigil? Saan ko ititigil yung summation? Balikan natin yung formula na gusto nating i-recreate. Meron siyang f double prime. So involved yung second derivative sa kanya. So ibig sabihin dito, kasi yung second derivative, yung nagbigay ng error term, so at least here I'll know that I'll keep f of x, I'll keep h times f prime of x para makuha ko yung f prime pumunta sa left-hand side. Tapos i-retain ko rin to kasi yung f double prime, siya yung nagbibigay nung error term. Okay? And yeah, I can just truncate everything by just replacing x by an arbitrary number c. Right? Yun yung sinasabi nung equation 6.7. Pwede mong i-ignore yung mga matataas na terms by just replacing x by a number c in the neighborhood of little x. Yun yung sinasabi nung 6.7. So let's do that. So we'll have this. Ito yung nanggaling sa Theorem 1 dun sa equation 6.7. Okay? And then here I can just transfer everything except for h times f prime to the other side of the equation. Lipat nyo lang yan. Lipat nyo lang din yung error term dun sa kabila. And then flip the equation. You'll get this. Remember, we're looking for f prime. So from here, all we need to do is to divide both sides by h. Okay? And by doing that, here's our formula, which is actually the same form as what we have before. I mentioned you can think of it as x1, this is x0, then h is the increment x1 minus x sub 0, which is essentially the formula we obtained from before, right? Ito yung nakuha nating error term, ito yung nakuha nating formula dun sa interpolation using 2 points. Though I think there's a typo here, dapat ito ay negative. Okay. Tapos pag kinompare nyo to dun sa kanina exacto, ito rin yung formula na nakuha natin. And from here, we can say that this is a finite difference of formula for f prime. So we can use this divided difference for the estimate for f prime, and we use 2 points. So this is a 2-point formula. This is a 2-point forward formula because we are approximating x or f prime of x, and we are using f of x and f of x plus h. So mula kay x, parang nag-move tayo forward para makupunta kay x plus h, which is the second point we use in our approximation. Kaya ang tawag sa kanya ay 2-point forward formula. And then also, if you look at the error is big O of h. Okay? So ibig sabihin, you can interpret it as the error vanishing to 0 as fast as how h goes to 0. Kasi kung mapapansin nyo, yung f double prime at c all over 2, constant lang yan. Constant lang siya. And times h. So really, nagdedetermine ng pag-vanish o pag-diminish ng error ay si h lamang. So that is the vanishing of the error is dependent on how h behaves. And since h lang naman yung factor dyan, so we can say that the error vanishes as fast as how h approaches 0. So we call this formula a formula of order 1. Kasi siya ay kasing bilis ni h to the power 1 nag-approach ng 0 yung error term niya. Okay? So in all, this formula is an example of a 2-point forward formula of order 1. And the nice thing about this derivation is we can extend it further to get formulas of higher orders using more points. And that's what I'll illustrate in the next few examples. But by the way, guys, do you have questions so far? Mukhang napahaba yung, yung introduction. I hope it's fine if I borrow some more minutes para matapos ko yung 6.1 and 6.2 para sabay kayo dun sa kabilang section. Okay, so let's look at 6.1. In example 6.1, ang pinapagawa sa atin ay mag-derive ng isang 3-point forward formula of order 2. Okay? And again, here, we'll take advantage of Taylor's theorem. So tingnan natin ano yung dapat approach natin. Una, we should use a 3-point forward formula. So starting kay x, mag-move ako forward with increment h. And then, dapat 3 points yung gagamitin ko. So, si x, counted na siya si sa. The next point we'll use is x plus h. And then the third point is x plus 2h. So, para nagmamarch tayo forward until we get 3 points using the same increment h. And then, dapat order 2. So, ibig sabihin, piliin natin yung truncation ni Taylor series in such a way na makakakuha tayo ng error term which has a factor of h squared. Okay, kasi ang kailangan natin ay order 2. Now, if we go back to Taylor's formula, let's devise our plan. Okay? Nagko-compute tayo ng derivative para kay f. So, ibig sabihin, magde-derive tayo ng formula kay f prime. So, we will work with this summation. Okay? Pero tingnan nyo si f prime. Si f prime may katabing h. So essentially, after transposing all the terms they don't need nakasama ni h times f prime, kailangan nating mag-divide both sides ng equation by h. Alright? So tandaan nyo yan, mag-divide tayo by h. Tapos sabi dun sa problem 6.1, dapat order 2 yung formula na ma-compute natin o ma-derive natin. So ibig sabihin, dapat ang pipiliin ko ay yung expansion hanggang sa h cube. Hanggang dito, sa may h cube. Kasi i-retain ko si x cube f triple prime of c all over 3 factorial. Tapos, remember, in the end ng derivation, dahil si f prime may katabing h, we need to divide both sides of that resulting equation by h. So, ibig sabihin, this guy will get divided by h, so matitira na lang ay h squared. And that h squared will be factored into our error. So gusto kong matira yung h squared na yon para makakuha ng formula of order h squared or formula of order 2. So kaya, kailangan kong i-retain hanggang dito. And that's what was done here in example 6.1. Kinuha ko yung expansion ni f of x plus h considering until h cube over 6 triple prime. Okay. Kaya hanggang doon yung kinonsider ko lang. I don't care about the rest of the terms there kasi hindi naman siya magma-matter later. Ito lang yung gusto kong i-analyze talaga para magkaroon ng idea about the error. And then, kailangan natin ay kailangan natin yung expansion para kay f of x plus 2h. Kasi remember, 3-point formula na resolve natin kanina na kailangan natin yung f of x plus 2h. Now, how do we get the expansion for f of x plus 2h? Well, we start here. Okay? Tapos lahat ng h, pinalitan ko lang by 2h. Kasi kung i-compare niyo yung left-hand sides, almost the same sila. Ang pinagkaiba lang ay yung h at saka yung plus 2h here. So, for the expansion, palitan nyo lang lahat ng h by 2h. So, here may h, napalitan siya ng 2h. Tapos, ito ay may h squared. Yung h dun sa h squared, napalitan siya ng 2h. So, we'll have 2h quantity squared, and that's where 4h squared came from. Okay. Also, here we have, in the third term, we have h cubed. So, after replacing h by 2h, we'll have 2h cubed, and that's where 8h cubed came from. Okay, ganun yung pagkuha ng expansion kapag ka meron ng multiplier si h dun sa left-hand side. Okay? Now, so that's it. That takes care of the expansion. Okay. And then, eto na yung paglalaroan natin. Now, remember, we can retain this kasi part sila ng posibleng data na gagamitin natin. Gagamitin natin si f of x plus h, si f of x plus 2h. Okay lang din na matira yung f of x's kasi part din siya nung sabi natin na gagamitin natin na data. The one with h prime, the ones with with f prime can be retained kasi kailangan natin yung formula para kay f prime. Tapos yung may mga f triple prime, for the sake of the error term, dapat matira rin sila. Okay? So the only unwanted thing here in the first few finite terms that we expanded would be this guys. Kailangan silang mawala. Bakit sila kailangan mawala? Kasi we're looking for a formula for f prime. And since we don't know f prime is, there's little chance that we have data pertaining to f double prime. So ayokong ilagay dun sa formula ko or isali si f double prime of x. Kasi nga kung wala akong data para kay f prime, most probably, wala rin akong data para kay f double prime. So it doesn't make sense to involve f double prime in a formula that computes for f prime. So kaya I want in my derivation that these two guys will vanish. So the idea there is it's like solving equations by elimination. So I'm gonna solve for f prime, but I want this guy to vanish or these guys to vanish. So ang pwede natin gawin, pwede ako mag-multiply ng -4 dun sa unang equation or both sides of the first equation. Multiply mo yan ng -4. And then we add the first or this product to the second equation. Tapos pag ginawa natin yan after multiplying -4, you'll have -4 h squared over 2 f double prime plus 4h squared f double prime, so they will cancel each other out. Okay, and that was what was done here in the next step. Kinuha yung f of x plus 2h minus 4 times f of x plus h. So I hope you guys saw why nagkaroon ng -4 doon for the sake ng cancellation ng f double prime. And then we'll get this. All right, pagka sinimplify natin yung sum ng mga right-hand sides, okay? Then we get this expansion. And then, ito na yung sinabi natin na in-anticipate natin na magdi-divide tayo by h. Yun nga lang, due to the addition of the corresponding sides of the equation, nagkaroon tayo dito ng 2h. So, i-divide ko pa rin both sides by 2h. So, this, guys, which you expect to be in our approximate formula or approximation formula, will be divided by 2h. And then, itong error term na to, madi-divide ng 2h. So, ang kakalabasan niya na lang ay... Hold on, parang may typo rito. So, tingnan nga natin. So, dapat -4. So, magkakaroon ako dito ng -4h cubed over 6 plus 8h cubed over 6. So, dapat ito ay 4. Tapos, dinivide by 2, kaya siya naging 2 dito sa baba. Okay? And then this is perfectly fine because we were told to compute for a formula of order 2. If you look at this error term, so ang mangyayari lang dyan ay ang f triple prime times 2/3 ay constant. So it will just really depend on h squared. And then yung contribution mula dun sa term na may h cubed will be insignificant compared to the contribution coming from the one with h squared when h rapidly goes to 0. Kaya pwede natin silang i-truncate na lang and say that the error is of order big O of h squared, which will give us as promised or as required a formula of order 2. So in summary, we can say na ito yung formula na nakuha ko. F prime is equal to this guy. And then the error term, the theoretical error term, will be coming from here. Copy it over, replace x by an arbitrary constant c. And that constant c, hindi pala arbitrary constant c, pero some constant c. And that c is between x and x plus 2h. Okay? Does the derivation make sense? Sana clear siya kasi ganyan yung gagawin nyo almost for the rest of the unit or the chapter. Okay? So, bibigyan ko kayo ilang points yung kailangan yung gamitin, tapos ano yung order. Tapos, bahala na kayong mag-solve paano ma-eliminate yung mga unwanted terms. Okay? But in the process, you see that we also calculated a theoretical error. So, ito yung theoretical error from which we can get a theoretical error bound. Kunin lang natin yung maximum ng f triple prime. Okay? Now, let me borrow probably 5 more minutes para lang ma-introduce ko yung example 6.2, which is very similar to what we have in example 1. Kaya lang dito, kailangan daw backward formula. So kung backward yung formula, ibig sabihin starting from x, gagamitin ko si x minus h at saka si x minus 2h. Kasi dapat pabalik naman yung lakad ko. That's of order 2. So here we'll need the expansions for x minus h, for f of x minus h and f of x minus 2h. Now, how do we get the expansion for those guys? Knowing only Taylor's formula. So from Taylor's, ang x plus h ay merong expansion na f of x plus hf prime of x plus h squared f double prime of x over 2 factorial plus h cube f triple prime of x over 3 factorial and so on. So if we want f of x minus h, ang gagawin lang natin, papalitan lang natin lahat ng h by negative h. So yung h dito, mapapalitan ng minus h. So that means this h here, oops, ay mapapalitan lamang ng negative h. Yung h dito sa h squared ay mapapalitan ng negative h, but we will have negative h quantity squared that will again give us h squared. So this is fine, that is retained. Yung h cubed, yung h sa kanya mapapalitan ng negative h, so we will have negative h quantity cubed, so that's going to be negative h cubed. So ito ay magkakaroon lang ng negative sign. Okay, so that's how we get the expansion for f of x minus h. And then also for f of x minus 2h, all we need to do here is to replace all h's by 2h. Right? So ganun yung idea paano nakuha itong mga expansions na ito. And again, we were told to find a formula of order 2. Again, for solving for f prime, we anticipate the division by a factor of h. So i-retain natin yung may h cubed. Para pag nag-divide tayo by a factor of h, matitira dun sa error term ay h squared. So I need to handle with care hanggang dun sa order 3 or degree 3 na term. And then I don't care with the remainders kasi hindi naman sila magma-matter dun sa formula. And then again, we can retain these two guys, retain these two guys. Of course, you want this to be retained kasi f prime yung hinahanapan natin ng formula. We reserve this for the error term. So the only unwanted terms would be these two guys. Kailangang mawala yung may f double prime. But again, we can we can get rid of them by multiplying both sides of the first equation by negative 4. And then after multiplying by negative 4, we add the resulting equation to the other equation. And then from there, do algebraic manipulations as what we did in example 6.1 in order to get this formula for f prime. And again, you will see that this looks very similar to what we got from 6.1. And then the error term will be this guy. Okay. Ito yung sukli dun sa expansion nito. Hindi ko na pala sinulat, pero pagka ito ay sinimplify nyo, sinama nyo siya dun sa algebraic manipulation, the error term will simplify to this guy. Okay. So basically, that's the general approach that we will use to derive finite differences. Okay. So and then this is hitting two birds in one stone. We not only got a formula for the derivative, but also we got an error bound, a theoretical error. Actually, not just an error bound, but the exact theoretical error term na magagamit natin for further analysis. So for Friday, we look at example 6.3 and probably look at, ano pa ba yung meron dito? Yeah, try to use this formula. So far, nagde-derive pa lang na tayo ng formulas. Hopefully, by Friday, we can look at how to implement these formulas. Pero simple lang naman siya. Pwede nyo siyang gawin sa Excel. Okay, no sweat siyang gawin sa Excel. Which reminds me, just an announcement, I might not be able to join you live on Friday. So I'll have something to attend to. So if I won't be able to make it, i-announce ko bukas ng siguro medyo paggabi na. So pardon the late email. Pwede nyo siyang buksan na lang bukas siguro mga 8 a.m. If you really want to get up early or antayin nyo yung announcement ko ng Thursday evening para alam nyo kung gigising kayo ng maaga kinabukasan. Because if I will not be able to meet you guys, then what I'll do is to just share with you the recording I'll make with my other lecture tomorrow. So para sabay pa rin tayo. Or what you can do is if you want to join us live tomorrow, you can also do so para hindi na kayo papasok sa Friday morning. Pero technically, hindi nyo naman kailangan pumasok ng Friday morning talaga kasi pwede nyo panoorin yung video, yung recording on demand. Okay? So that's it. So para lang kung alam nyo kung gigising kayo ng maaga sa Thursday, sa Friday. And then also again, problem set number 1 is now live on Canvas. Make sure to read the instructions carefully because I made some modifications. I announced last time that you'll have 4 problems to solve. Now I decided baka masyadong marami kayong ginagawa this times. So I decided to require problem number 1 and then you will just choose 2 more problems out of problems 2, 3, and 4, making the total number of submissions or required problems to 3. Tatlo na lang yung ipapasa nyo. Pero yung may mga sub-items kasi mga questions. So, yeah. So, required si number 1, pili kayo ng dalawa between or among problems 2, 3, and 4. Do that. Then that would be your problem set. You'll have until November 1st, right before midnight, to submit your answers. Okay? With that, sakto 9:30. Any questions? Any concerns? Oh, yes, Noriel.
Sir, ask ko lang po if type written po ba yung sa problem set or handwritten?
Yeah, good question, Noriel. Actually, it doesn't matter. Pwedeng typewritten kung mas convenient to typewritten or pwede namang handwritten kung mas convenient sa inyo. Basta ang ina-avoid ko lang talaga sa typewritten ay yung magka-copy paste lang kayo. So, please do it on your own. So, and wala naman akong i-require. So, posible kayo nang bahala kung ano yung mas convenient sa inyo. Dun sa essay part, siguro okay na handwritten kasi mas madali sigurong isulat kung handwritten. Tapos dun sa computation part, siguro kung mas convenient siyang typewritten kasi kung ganun din naman, kailangan nyo ng mga graphs doon or kailangan nyo ng kung gusto nyo i-copy-paste lang yung result nyo mula sa MATLAB o mula sa Python, then that's fine. Hindi ako strict sa format. So, pwede ring mixed format. Pwedeng sa problem 1, handwritten, sa problem 2, typewritten, or yung problem 2, pwedeng some parts are handwritten, some parts are handwritten, some parts are typewritten. I don't care. Basta nababasa ko, alright? At saka wag yung copy-paste mula sa gawa ni classmates. So, hopefully, gawin nyo siya ng kanya-kanya. I mean, pwede kayong mag-group study, pwede kayong mag-consult with each other, pero pag sulat nyo ng problem, nung sagot nyo, please do it independently para at least makita ko kung paano nyo naintindihan yung produkto ng inyong collective effort. Okay? So, yun. And then please acknowledge those who were part of your study groups or any material that you used. There should be no shame to that. Lagyan nyo lang ng credit dun sa submission. Okay? So wala naman submission pag sinabi niya, sir, may nakita akong program mula sa internet, ginamit ko siya, and that's perfectly fine. Hindi ko naman kayo pinagbawalan to use resources. So my only request is please acknowledge them para rin masanay kayo na we are giving credits to where credit is due. Okay? Any other concerns? So hopefully kaya nang i-submit yung 3 problems by November 1st. Tatlong problems, I think you still have 5 days, 27, 28, 29, 30. May 31 ba? 31 and 1. So I think you'll have 5 or 6 days to finish it. So try to finish 1 problem per 2 days. So you'll be in a good shape to submit it by the deadline. Okay? Tapos yung ibang problems dyan, yung program na gamit nyo na sa lab, so recycle lang. So yeah, I hope this reduction in the number of items will make it easier to bear for you guys. Other concerns? Questions? So kung wala na, so thank you for coming today. And then either we see each other on Friday or we'll see each other next week na. Okay, bye guys.